Hi, welcome to the second part for the logical effort where we discuss path delay using logical effort. But before that, in the previous lecture in slide 30, I might have indicated or misspoken in representing the G for the inverter and when I compared it with NAND and NOR gate. So what I said is that the G for the NOR is less than the G for the NAND, and the NAND less than the G for the inverter. Uh, so what I meant by it is that I meant to say that the current capability, the, the strength of the NOR gate is less than the strength of the NAND gate is less than the inverter. But in terms of numerical value, we know that G for NOR gate, okay, is for two input is 5/3, and G for NAND gate, all right, is 4/3, and G for the inverter, right, it is 1. So in terms of numerical value, obviously for the NOR gate is larger than the NAND, and the NAND is larger than the inverter. But in terms of current strength, okay, it is the reverse. The NOR in terms of the current strength is less than the NAND, and the NAND is less than the inverter. In terms of current strength, the inverter is the strongest. Okay, so I want to clear that. But to say it another way, the G is inversely proportional of the current strength. Oops, of the current strength. Okay, so that's to clarify what we said in the last lecture. Okay, and let's go back to this lecture now. Okay, so let's now discuss the path logical effort, the computation of the logical effort for path delay. Okay, basically what we have done so far, let me split the screen here into three parts. What we have done so far, we computed the delay for one stage, okay? And just to remind ourselves that the delay was expressed in terms of the effort delay, which is F plus the parasitic delay. And we said that the effort delay equals the logical effort times the electrical effort plus the parasitic delay. Okay, so that's the delay for one stage. Now what we want to do is to extend this concept into what we call path, multi-stage path. So in this case, I'm going to have a gate followed by a gate followed by a gate, etc. And this will be n stages, okay, or n gates or n levels, whatever you want to call it. Okay, now obviously what we will do now, we want to extend this to the computation for, so this is path which consists of n stages, okay, right? So now we will extend the same argument here. So here's what we'll say, that the path delay is going to be equal to path effort delay plus path parasitic delay. Okay, and we will call this as the delay for the path equals the effort. Notice that the F similar to this F here. okay, plus the parasitic delay. Okay, and now what we will say that this path delay, okay, it is, so this is the path effort delay. It is a summation of the effort delay for the stages. When we optimize all the stages, here is what we will say, that all the stages, stage 1 and stage 2, stage n, they will all be equal and equals f hat. Okay, and what we will try to do here is to find out what is this f hat, which is pretty much the stage effort delay. So what is f hat? Okay, well, f hat is defined as follows. We will define now the path effort, as the path logical effort, right, times the path, we'll call this branching effort. Okay, so this is path effort, branching effort. So this is the path effort, and this is the path logical effort, and this one is the path branching effort times h, which is the path electrical effort. You can see similarities in the definition. Okay, so since here we have defined F equals GH, and there was a B here, by the way, but we always assume B equals 1, which is the branching for one stage. So ignore this B for now, but I'm going to just say there is a parallelism between this definition and this definition, between the stage and the path. Okay, so the path effort, the path effort, which is this F here, equal the path logical effort, the path branching effort, the path electrical effort. These three things. Okay, let's define those now. But before we define them, let's understand the link now. Okay, so we define this. Why? Now remember, we need to find out this f hat, because it will help us in finding the computation for the path. So now f hat f hat equals the nth root for the path effort. Oh, that's good. So now once I find out this one, once I find this one, then I use it for this equation. More beautiful also is that f hat itself is equal to g b h for every stage. Okay, and we know that the g is for every stage. The g is what? The g is the logical effort for the stage or for the gate. The b is the branching, and we will define it. But for now, we'll assume it's 1 for simplification. And h is what? H is the electrical effort per stage, C out over Cn. Okay, now so we need to understand now, what are these quantities? What is G? Well, G equals, since these stages here, every one of them has G1, G2, Gn. Every stage has a value, so I say it is the multiplication of G1, G2. You multiply the G's for all the stages. How about the H? The H here equals, since I have here a C out at the end of the path and a Cn at the beginning of the path, then I'll say the H equals C out over Cn. This is for the path. Notice this is for the path. Okay. Now, how about now B? We'll assume it is 1 for now, and we'll see later on we'll discuss branching. So now I can compute those, plug in f here, I can compute f hat, and from this f hat I can compute the delay for every stage. And also, because this is f hat will be known, I can plug in this f hat here. In fact, now we can update the equation. This equation, we can update it now. We can say that the delay, okay, the delay equals the delay of the path equals. Now notice df now can be replaced by n times f hat plus the delay, the parasitic delay. And I know that f hat equals the f raised to the nth root plus p. Okay. Now, all of this is I'm gonna lay. I'm laying out the equations without any proof. If you want the proof, you can consult your textbook and for proof. But we will use these equations to compute the optimum delay and sizes for a path. And let's take an exercise which will illustrate all these numbers for us and make it very clear. Okay, so let's take an example to illustrate the calculation of the path delay. Now, here's an example that you might see in the exam. This is a path where the number of stages is 1, 2, 3, 4. So n equals 4 stages. Now, the Cn for this path equals 10, and the C out equals 20. Okay, right? So and the logical effort for every gate for the inverter, it is 1. For the 2 input NOR gate, 5/3. For 2 input NAND gate, 4/3. For the inverter is 1. So to compute the sizes and the delays, the very first thing I need to do is to compute f hat. Okay, so for f hat to be computed, I need to compute f so that I can raise it to the nth root. Now, what is f? F equals g, b, h. So let's compute those for the path. So now, G for the path equals what? The multiplication of G1, G2, G3, and G4. Now, and that is equal to what? 1 times 5/3 times 4/3 times 1, and this is equal 20/9. Okay, so that's for the path. Now, let's compute. Now, let's compute now the H equals what? Well, H equal C out for the path over Cn, and this is equals to 20/10, and this is equals 2. So this is the 20/10. Okay, now this is the H for the path. Now let me compute now the B. The B will assume it is equal 1 for now. Okay, all right. So now F equals what? F equals 20/9 times 2 times 1, and that is equal 40/9. So now F hat equals what? The nth root, which is n is equal to 4, 1/4, for 40/9, and that comes to be 1.45. Okay, so what's the delay for the path? The delay for the path equals n times f hat plus p, and this p is the parasitic for the path. The parasitic for the path is p for the inverter p1 equals 1, p for the NOR gate equal 2, p here equal 2, and p equals here 1. So now add 1 plus 2 plus 2 plus 1, that is equal to 6. Okay, so D equals 4 times 1.45 1.45 plus 6. That is the path for the delay. Now we need to find the sizes. Okay, so we find the sizes by applying this f hat on the gate, right, equal h g times h times b, and we know b equals 1. Okay, so let's start with this gate here, because I want to find these sizes x and y and z. So we'll use this gate here. This gate abides by this electrical effort. So f hat equals GH, and this is for the inverter equals what? For the inverter, G equals 1. What's the H for this inverter? For this inverter, H equals the output load over 1, over 10, sorry, times F hat, which is 1.45, because F hat, I just computed it, which is right here. So this means X equals what? X equals 14.5. That's the size of X. So this X equals 14.5. Now I need Y. Again, I apply this electrical effort. I apply this electrical effort equation on the NOR gate, which is gate number 2 here. This gate here. So electrical effort GH, which is equal 1.45. What's the G for the NOR? It's 5 over 3. Right? Times what? Times the load of this gate. The output load is Y over the input gate capacitance here, which is the X. Okay, I know the X value, right? So now I can find out what is Y. So Y can be easily computed as 12.64. Okay, now I need to find Z, right? So Z, I can find it out by looking at this, examining this gate. Okay, so this gate equals F hat equals GH, and F hat is 1.45. G for gate 3 is 4 over 3. Okay, H is what? H is the load here, the output load, which is Z over the input load here, which is Y. So Z over Y. Now I know Y. I can plug in this value here. I know all the numbers, and I can find out Z, and Z turns out to be 13.77. Now notice I started from the path from this side all the way to this side. Let's see. I started from this side all the way to this side. Let me see if I can. Okay, I started this way, right? There is no harm. I can start from the other way. Okay, in fact, it might be better for me in the assignment or the exam to start the opposite way, from the output to input. For example, if in the exam asked about Z, probably the other way is better, because now to find Z, I had to find Y, and then to find Y, I had to find X. But if I start from this side here, I will find Z very quickly. So let's start from the output side. Okay, so let's start from the output side. So the output side here, examine this output side, which is this inverter. This inverter, F hat equals what? GH, right? F hat is 1.45. G is what? 1 times H is what? 20, the output load, over Z. I can find out Z very quickly, right? Because it's 20 over 1.45. Okay, and similarly, and from Z I can go back to the this gate to find out Y and then X. So in other words, you can approach finding these variables either from the input side or the output side. Okay, and if you do it either way, your computation should end up and result with the same numbers for X, Y, and Z. Okay, let's go back to the slides here, and let's see if we missed something. So this is the example that we have done. Now, so far, we have not discussed the branching effort. What the branching says, you see, in every stage, we said F equals GH. And in fact, there is B here, which is the branching. What does branching mean? It means that the gate drives more than one branch. Like in this case, the gate drives this branch and this branch. So for this particular gate, F equals what? G H B, and B in this case equals 2. Okay, so now for this gate, B equals 2, and for this gate, B equals 1. For the entire path, now it is equal B1 times B1, this one, and this is B2, B1 times B2, which is this one here. Okay, and this is equal 2 times 1. Okay, so if I may now compute the G here for this path, it is G1 times G2, which is 1 times 1, because both are inverters, and H equals what? H equals 90 divided by 5, which is equals what? 18, right? 18. Okay, now for this particular path, if I want to find the path effort, it is equal GHB, which is equal to 1 times H18 times B2, which is equal 36. Okay, now having said that, let's continue for this side. So therefore, the F hat equals what? The optimum F equals what? Equals F raised to the power 1 over N. N here equals what? 1 stage, 2. Therefore, N equals 2. So this is 36 raised to the power 1 over 2 equals 6. So the optimum F hat equals 6. Okay, so now the branching effort, because I have this node goes to 2 equal paths here, that's called branching effort, and this case the B for it equals 2. Let's take a more broad example. Let's take this example. Okay, so let's discuss this example where I have this circuit. Clearly, there is branching going on here. So for this gate over here, oops, let's redo this. G1 for this gate is 4 over 3, and what? And the branching is 2, because you notice, oh sorry, 3, because notice that this path goes here and here and here. Now let's go to this gate here. G2 equals what? It is equal 5 over 3. All right, 5 over 3, and the branching for this gate, it goes to here and here, that's equal 2. And for this gate here, final gate, so this is stage 1, stage 2, stage 3, therefore N equals 3. And for this gate here, G equals 5 over, or G3 equals 5 over 3, and B3 equals 1, because we go to one gate. Okay, so for the path, G equals what? 4 over 3 times 5 over 3 times 5 over 3. Okay, and this is equal 100 over 27. Okay, so now for the H, it is equal to 45. Okay, divide by 8. Okay, now for this is H. For the branching, for the path, the branching B equals, okay, for this gate it is 3 times, for this gate 2 times, for this gate 1, okay, and this equal 6. And therefore the F for the entire path equals what? GBH. Okay, so this is equals to 100 over 27 times the B, which is 6, times the H, which is 45 over 8. Okay, and that comes to 125. Now let's now compute F hat. F hat equals the nth root of F, and that comes 125 over 1 over 3, and that comes to 5. Okay, now I can find out XYZ easily either by going this side or this side. It doesn't really matter. Let's start from the input to the output. Okay, so let's take the first gate here. Okay, let's take the first gate here. Okay, so to find X, F hat equals GBH. Okay, F hat equals 5. G for this gate is 4/3 times the branching for this gate is 3 times the H is X/8. X the output load over 8 for the input load. Now you can cancel this with this, and clearly X equals 10. Okay, so that's that's the very first variable we solved. Let's try to solve variable y, and I can look at this gate from here or here. So let's take a look at this gate here to solve variable y. Okay, so again, this f hat equals what? G B H. Okay, so f hat, which is 5, g for this gate here, g is 5/3, and the branching is 2 times h, which is y over x, which is 10. Okay, now I can cancel this with this, and clearly y equals 15. So now I have used this branching business to also optimize and calculate the optimum delay for multi-stage path using the logical effort. Okay, let's go to the slides now, and let's go to the slides. And so this is the there and the computation. Okay, and now let's see what is the best number of stages given here is a problem. Given that I have any number of inverters and I have a load of 64, what is the best number of inverters that gives me the least delay? Okay, well, since we have inverters, I can so number of inverters, let's assume it is n. Okay, and I know that inverters, okay, they have this nice feature. So this is n of them. The G equals 1, the P equals 1. So the intrinsic delay can, if I have inverter, is n. And if I have the load of the inverter, the input load is 1. So if I have an output load here of 64, right? 64. So then the H equals 64/1. So this is I can see the F equals what? G B H. I know that the H is 64, the B is 1, no branching, and the G is 1 as well. So F equals 64. So F hat is what? F hat is 64 to the nth root, 1 over n. So this is what I have here. Okay, times n, because I have n stages. Okay, so the delay is n times 64, 1 over n plus n. So the question is, I need the optimum n. Okay, I have here n as variable. Recall in the previous examples, n was fixed to me. 3 stages, 4 stages, but here is n is variable. I need to optimize n and the delay. So what do? I go experimentation now. So what happened if I have one inverter delay, one inverter? Well, I get a delay of 64. Okay, let's have 2 inverters, which means n equals 2, right? The delay is 18. Let's have 3 inverters. N equals 3. The delay is 15. Let's have 4 inverters, right? And n equal 4, the delay is 15.3. We'll see that the delay decreased up to 15, and then it picked up for 4. So obviously the optimum number of delay is having 3 inverters. So in fact, it's a classical problem of finding the best number of stages to find or to optimize the delays. So which leads us to this question: suppose I have a logic of n1 stages, n1 levels. Then I added n minus n1, just inverters, so that I have the entire path of n stages. So if I compute the delay for this path, obviously I know that the delay for this thing is, for this part, is n times f to the power n, the nth root of f times n. Then the delay for these extra inverters, which is this one here. Okay, and if I optimize this, I'm gonna get, assuming that rho here is the nth root of f, I'm gonna get this closed form as the optimum value of rho. Okay, now this leads me to form which has no closed solution, right? Because I have to use numerical methods. Uh, uh, let's assume that the PN, which is the parasitic of these inverters, and these are zeros, we will find that the optimum rho, which is the optimum f hat, is 2.7, which is the E number, okay, the natural number. Now, that is really not practical to assume that the parasitic is zero. More applicable is to assume that the Pn, the parasitics, equal 1, right? And that leaves us that the optimum rho equals 3.65, and which means 3.59, sorry, which means that the optimum f hat is about 3.6, right? Assuming that the parasitics equals 1. And that is close to what we found out in this example when we did uh, uh, this experimentation here. So notice we got 3, which is kind of close to 4, and that's why people they kind of approximate this to be f hat equals f hat. I'm sorry. Let's back go to this one here. Uh, Okay, so that's why people would like always to use f hat close to 4. Let's look at the last diagram here. What we are plotting here is that delay, right, versus the number of stages. Now the delay is normalized with the optimum delay. Okay, with the optimum delay, and this is normalized with the optimum number. Okay, so notice that as I increase number of stages, I'm getting less and less delay. Then at some point, the delay increases, and the question is, why is that? Well, and the reason is that the delay, notice, is equal to n times f nth root plus um, some kind of this parasitic. And if I use inverter, okay, it will be some kind of like an n here. Okay, so notice that this term diminishes with large n. Okay, but it increases with small n. This term increases with large n, diminishes with small n. So let me just so you can see that there are really this is the typical optimization problem. Some factors n f to the power 1 over n plus n. I'm assuming inverters design. Some factors will be so this is the delay. This factor diminishes with large n. This and this factor diminishes with a small n. So you can see that the delay goes up to a point where the other factors start to pick up and increases the delay. And this is right here is about our 3.59 what we saw in the previous. So the other observation here is that there is a plateau here. There is a plateau. Yeah, it's not a plateau. The curve somehow moves slowly. So this rho or optimum f hat can be between 2.6 and 2.4 and 6 and within 15% of the optimum delay. That's why people say, okay, if it is this case, let's approximate this 3.65 here. We'll approximate it to 4. And that's why you will see that the optimum f hat or rho, people prefer to use 4.0 even in this textbook. Okay, with this slide, I conclude this section. The rest of the section is reading material. There's a reading example. You can read it on your own. And thank you very much.